The next problem we will look at in the topic of greedy algorithms has the algorithm known as Huffman's encoding algorithm, which is a classic, very beautiful, very simple and nice greedy algorithm that solves a particular encoding problem. Okay, so let's look at the settings. The setting is that we have some file. You think of some data file which has a sequence of symbols. Okay, symbols, a sequence of some characters. So let's say a file has something like some characters, a whatever, B, E, C, A, D, okay, whatever. So we have some sequence, a file is made up of a sequence of these characters. Okay, and now we need to store this file, and so we of course need to store it in a binary form, right? So we need to store it using zeros and ones, right? So we have to have some way of encoding the file in binary, right? So the problem we'd like to answer here is how can we encode this file using the smallest amount of bits, the least amount of bits, right? So we'd like to have the most possible compressed version of this file, the least amount of bits to store this sequence of characters. Okay, so so maybe let's write out our symbols. So we have symbols, let's say we have A, B, C, D, E, F. Okay, let's say for this example that our file only has these characters and nothing else. Okay. And also let's say we'll also count the frequency of each of these symbols. So let's say A occurs 20 times in the file, or 20,000 times. So let's say for this example, it occurs 20 times. So it's a small file. Let's say B occurs 12 times. C occurs, let's say, 10 times. D occurs 8 times. E occurs 4 times. And F occurs 3 times. Okay, so just let's say this happens. Okay, so one way to encode it is what is known as a fixed length encoding, right? So a fixed length encoding. In a fixed length encoding, basically what happens is that each symbol gets the same amount of, or each symbol uses the same amount, the same number of bits. Okay, so over here we have 1, 2, 3, 4, 5, 6 symbols, right? And if we have to encode 6 different symbols, we would in this case require at least 3 bits, right? So what we could say, so let's say our fixed length encoding here, that's whatever, the actual encoding doesn't matter. It's a number of bits that really matters. So let's say 0, 0, 0, we give encode A as 0, 0, 0 by these 3 bits. And then we encode B as 0, 0, 1. encode C as 010, D as 011, E as 100, right? And F as 101. Okay. So, right. So if we do something like this, what is the size of our file, right? Or the number of bits required to encode the file is simply we have A occurring 20 times, and each time it requires 3 bits. So it's 20 times 3 bits for A, plus 12 times for B. B occurs 12 times, and each time it takes 3 bits. C occurs 10 times, 3 bits, and so on, right? E occurs 4 times, 3 bits, and F occurs 3 times, 3 bits. So this works out to be 171 bits, right? So our entire file would take 171 bits using this fixed length encoding. Okay. Now, what people thought is, why do we need fixed length encoding? Okay, let's try and reduce this file size by using what is known as a variable length encoding. Okay, a variable length encoding. So in this, the idea is the symbols like A and B and so on, which occur many times, let's give them encodings with a few number of bits. Okay, so maybe let's consider a variable length encoding. Okay, this is some hypothetical one. Let's say we encode A simply using the bit 0. Whenever I see a character A, I'll replace it by 0. Okay, and maybe B will encode 10, C will encode 101, D will encode 111. Okay, so this is some hypothetical variable length encoding that I'm writing out. Okay, okay, but the idea here is the symbols which have the high frequencies, we use a fewer number of bits. Okay, so what that would mean is that the file size, because we are using less number of bits for symbols that occur many times, the space required for those symbols would reduce, right? Our file size would reduce. So if we compute the same quantity, number of bits required to encode the file, in this case, would be A occurs 20 times, but each time you're just using 1 bit, right? B is occurring 12 times, and each time here we are using 2 bits for B. Okay. C is occurring 10 times, but each time we are using 3 bits in this encoding. And D is occurring 8 times. Each time we are using 3 bits here for D. Then E is occurring 4 times, and each time we are using 4 bits for E. And F is occurring 3 times, again using 4 bits. Okay, so how much does this work out to? I think this works out to 126 bits, I think. Okay. All right. So we see that it's a significant reduction in the file size, right? Don't look at the number of bits reduced, but it's really the fraction, right? What is the percentage of the file size that you have reduced? Okay. So yeah, so it looks like these variable length encodings is actually a great idea, right? It makes complete sense that it's okay maybe to give larger encodings for symbols that occur infrequently, right? So here, in fact, we are using even 4 bits for some symbols, but even by doing that, it more than compensates by having small encodings for the high frequency symbols, right? So, right. So how can we, so the problem is, can we find such a variable length encoding, which is the best possible variable length encoding in some sense, right? Which gives us the least, the smallest file size. Okay. So yeah, so how do we do this? Okay, so while looking at this variable encodings, we realize that there is actually some issues with these. There are some problems. Okay. The problem occurs while decoding an encoded file. Okay, when we have these fixed length encoding, decoding a file is straightforward, right? So if we have some file like this, right? Whatever, a series of sequence of bits, when we have a fixed length encoding, we know that the first 3, they are always have, each character corresponds to 3 bits. So this would represent one symbol, this would represent the next symbol, this would represent the next symbol, and so on. Okay. And we'll have a table for each sequence of bits, so what is the corresponding character, and we can decode our file easily. Okay, but now you see that when we have this sequence and we have variable length encodings, we have a problem. Okay, so recall, yeah. So here we had, for example, just look at these 2 encodings. A was 0 and B is 1, 0. Okay, so now yeah, so maybe look at, let's focus on this part. Okay, so let's say B is 1, 0 and C is 1, 0, 1. So let's say we went on decoding. So we came to this point, let's say over here, and we saw a 1 and we saw a 0, right? And now we are faced with the problem, this 1 and 0, should we write this, take this as 2 bits, take these 2 bits as representing the symbol B, or should we look at the next, scan the next bit, and we see there's a 1, and maybe we take this and treat it as a C, right? So there is an ambiguity here. We don't really know what is the what does it correspond to, right? We'd like our decoding also to be straightforward and unambiguous, right? Where we don't have to face these choices, right? We don't want to maybe first try taking this as B and seeing if we end up with some inconsistency, and then backtracking and taking it as the next symbol and all. That would really, really make the decoding expensive, right? We would like to have a um, direct and fast decoding way to decode also, right? So to avoid this ambiguity while decoding, we will require the encodings, the variable length encodings, to be what is known as, what we call as prefix-free encodings. Okay. Okay. So if we look here, we go back to this example, the problem with this encoding was that one of the encodings, 10, is a prefix of another encoding, 101, right? So when this happens, when one of the encoding is a prefix of the other encoding, whenever we see this code, right, we are not sure if it corresponds to the symbol corresponding to this encoding, which is B in this case, or if we need to go ahead and scan the next symbol and if it will correspond to this symbol, right? So really the problem here is occurring when we have one encoding being a prefix of another symbol's encoding. Okay, so we want to avoid these kinds of encodings, and that happens in these prefix-free encodings, right? So in a prefix-free encoding, we'd say that the code, the encoding, right? The encoding of a symbol cannot be a prefix of the encoding or of the code of some other symbol. Okay. Okay, so this is what we are going to require of our variable length encoding. Okay, and once we have this, our decoding becomes unambiguous. Okay, because the moment we hit a pattern which corresponds to a symbol, we can directly output that as that symbol in the decoding, because we can be sure that by adding more bits to this encoding, we'll not get the code of some other symbol. Okay, because the codes are prefix free, our decoding now becomes unambiguous. All right. So we'd like our codes to be prefix free. So that is one thing. So these prefix free code, it turns out they have a close relationship with binary trees. Okay, with some types of binary trees. Okay, so let's think of binary trees here, where let's say the left branch, let's think of it as representing the code 0 and the right branch as the code 1. Okay, so let's maybe look at something like this. Okay, a binary tree of this form. Okay, so now what does an encoding so maybe if you go back to the same example, here we had our encoding of B was 10 and C was 101, right? So if we see here, what we have is 1 0, right, and again 0 1. Okay, so what we had here was that 1 0. So when we came down 1 0, this represented our symbol B, right? And 1 0 1, this represented our symbol C. Okay, and this was problematic, right? This was not a prefix-free encoding. Okay. So what would prefix-free encodings look like in this binary tree? If we had a prefix-free encoding, what constraint would we have to impose on this binary tree? Okay, well, clearly what we'll need to impose is that these symbols here cannot occur as internal nodes, right? So what we will require is that all the symbols, all the symbols should be at the leaves. Okay. When this happens, this is basically a prefix free. This corresponds to a prefix free encoding, right? Do you see this? Okay. That would avoid all such scenarios, right? Okay. When one symbol is a descendant, right? When one symbol here is a descendant of some other symbol in the tree, that would mean that it is not prefix free, right? So we don't want that to happen. So we'll require that all the symbols occurs, sorry, all the symbols occurs as leaves. Okay. So we probably have B here and something like that. Okay. Right. And the prefix is, right, the prefix of a symbol, right? A prefix of a symbol would be simply the codes encountered when we go from the root to that symbol, to that leaf. So, right, while going to B from the root, we first have 1, 0, 0. That is the encoding of B, right? And 1, 0, 1 would be the encoding of C, and so on, right? So, um, what we would like is that we have, if we have n symbols, we would like to have this binary tree which has n leaves, right? Okay, we are not saying it's a complete binary tree. It's some binary tree, but it has n leaves, and the path from the root to the leaf would tell us the encoding of that particular symbol. Okay, and I hope you see that this constraint here, that all symbols should be at the leaves, that will ensure that our encoding is indeed prefix free. Okay. Okay. So we have this binary tree that we are looking for, such that the left branch is 0, right branch represents 1s, and we have symbols at the leaves. Okay. Another condition that we will ask for is that the tree is full. So the binary tree is full. It's a full binary tree. Okay. So do you remember what a full binary tree was from long time ago? Okay. A full binary tree, it's basically, it requires that no internal node has exactly one child, right? We cannot have something like this, in fact, right? Because this is an internal node which has exactly one child. Okay. So we'll not, so what we'll require is that no internal node has exactly one child. Okay, and I leave it as an exercise for you to think about why this is the case. Okay, why do we want this? Okay, basically you can get a better encoding, a better tree by doing a small change if you have something like this. Right? Uh, if you have a internal node which has exactly one child, you can do a small change to that tree and get a better encoding. Okay, so I think now we are kind of in a position to state our problem a little more formally. Okay, and we'll use this notion of trees that we have developed to define our problem. Okay, so the input to our problem here is n symbols, right? We have n symbols, and with given frequencies, right? So symbol 1, let's say, has frequency f1, symbol 2 has frequency f2, and the nth symbol has frequency fn. And the output that we would like, well, informally speaking, it's a prefix free encoding, right? It's a prefix free encoding of optimal size. Okay, so this is not very precise. It's just so we have a prefix free encoding, which optimal size, what we mean by that is that file size that we calculated initially, that has to be the least, right? So we can try and write this in terms of what we have just developed. So we are basically looking for a binary tree, right? A binary tree T with n leaves, right? We have n leaves corresponding to the n symbols, right? And such that the cost of the tree will define a cost of the tree, okay, which will basically be the file size. Right? So what will be the file size in terms of these frequencies? Okay, so basically for each symbol we have to compute the product of its frequency with the length of its encoding, right? That's what we did for the initial example. What would be the length of the encoding in this case? Well, the length of the encoding would simply be the depth of the leaf in the tree, right? If I had whatever, if I had a leaf sitting over here and I had some leaf sitting over here, this, for example, this depth here, maybe 1, 2, 3, 4, that would be the length of the encoding, right? So what we'll denote this as the quantity, some quantity di, okay, where fi we know is the frequency of the ith symbol, but di is basically the depth of the ith symbol in the tree, right? In this particular tree. Okay. And so this, if we sum this up for each symbol, that would represent a file size, which we'll call as the cost of this tree. Okay, it's parameterized by the tree, of course, right? If we consider a different tree with a different arrangement of the leaves and the symbols, then the cost of that tree would change, right? That would represent a different prefix-free encoding with a different cost. Okay, so we are looking for the prefix-free encoding, which has the least cost, so such that this cost, this is minimum. Okay. We are trying to minimize this cost function on trees. Okay, so You see that this is a combinatorial, again, a combinatorial optimization problem where we're trying to find the object we're trying to find is this binary tree, right? We're looking for a binary tree which has the minimal cost. Okay, so we'll see how we can go about doing this in the subsequent videos.